Hello guys, I'm Anmol Panda from the Programming Club of IIT Madras. So today I'm here to discuss the solutions of Codeforces round 818, that was the division 2, conducted just few hours back. I was able to solve problems A, B, C and E during the contest, and I'll be discussing the solutions to problems A, B and E. And in the latter part of the video, problems C and D will be discussed by a friend of mine, Chehal. So yeah, let's get started with problem A. So we can open from A. Yeah. So the question is you have to find all pairs of integers a comma b, and this is an ordered pair where both are less than n, and LCM AB by GCD AB is less than equal to 3. Both are they're ordered pairs, so 1 comma 2 and 2 comma 1 both are being taken. So yeah, so the first thing you need to understand is that if you write LCM of a comma b, by the definition of LCM, this is a multiple of both a and b. Okay, so we can write this as some k times a or l times b. Okay, so let me write it as k times a. Okay, and also one thing just before we start, let us assume a is greater than equal to b. Now you might ask that this might not be the case. Yeah, that's true. So what would happen is if we get a pair a comma b, then b comma a is also a valid solution. So we can kind of multiply the pairs by 2 at the end, for getting the total number of ordered pairs. So so the problem is identical for these both. So without loss of generality, you can assume a greater than equal to b. So yeah, so LCM of AB is equal to k into a, where k is an integer. That is something uh, which is to be understood, that k is an integer and greater than 0. Now if you take GCD of a comma b, GCD of a comma b is a number which divides both a and b. So what we could write this as, a by t, where again t is greater than 0, t is a natural number basically, because a by t will divide a, and since it's at GCD, this should divide b also. So yeah, this is how we can write LCM and GCD. The reason of that, the motivation of writing it in this form is that here you see that the ratio of LCM and GCD is asked. So my aim was that you write them in such a way that this a gets cancelled and you have small numbers now. Now you have, like, when you divide these both, let us just move one step ahead now. When you divide these both, you get k into t, and they have given this ratio is less than equal to 3. Now you see this problem is actually much more approachable, because you can exhaust all cases for k and t. Like, you can check for k equals 1 what are the possible values of t, k equals 2, and maximum k value can go to 3. It's obvious by the inequality. So the motivation of writing it in this form was that I can cancel out a, and I have something like a constant type of thing with which I can exhaust all cases, because the number given here is a very small number. Okay, so in this case we can write all the possible cases. So let us take k equals say k equals 1. So if I write the ordered pairs directly, k equals 1 comma 3 is possible, 1 comma 2 is possible. For k equals 1, these both are possible, and for k equals 2, 2 comma 1 is possible. For k equals 3, 3 comma 1 is possible. Now let us just see for which of these k and t is our solution feasible, because we have initially assumed that this a greater than equal to b. So whatever k and t we get should satisfy that initial constraint. So if k equals 1 comma 3, that is basically telling that LCM is A and GCD is A by 3. Okay, so in this case, since A is greater than equal to B, see, so one number we know here is A. So LCM of A comma something is A. LCM of A comma something is equal to A. So basically this something is a factor of A. This something is a factor of A. So, again we can exhaust all the factors. Can A by 2 come here? Yes, A by 2 can come here. But you see, then the GCD of A comma B will not be A by 3. It will be A by 2. Because A by 2 divides A and A by 2 divides A by 2. So we can go for A by 3 then. And A by 3, if you see, it satisfies both these constraints. So you can write, so one of the possibility of A and B will be A comma A by 2. And this is actually fine because we have assumed A is greater than equal to B. And here also we are getting the same, A is greater than equal to A by 2. So this is a possible solution. So we can just note down all the possible solutions somewhere. So one possible solution is A comma A by 3. Now, K equals 1 comma 2. It's exactly the similar. Just here a 2 will come now. And you will get LCM of A comma A by 2. Just as we got A by 3 here for K equals 1 comma 3. For K equals 1 comma 2, K comma T, you will get A comma A by 2. Okay, and also just a mistake from my side. Here K and T can both be 1 and 1 also. I'm sorry, I just forgot the most trivial case. But yeah, K and T can both be 1 comma 1 also. So if K and T are both 1, it basically saying LCM of A comma B is A, GCD of A comma B is A, which implies A comma B have to be equal, and that they have to be equal to A itself, because both the LCM and GCD are equal to A. So we have another possible solution, A comma A. Now let us take K comma T equals 2 comma 1. So in that case, what will happen is, we'll get the GCD to be A and we'll get the LCM to be 2A. So GCD of A comma B is equal to A, okay, and A is the larger number, okay, so B has to be smaller than A, but A divides B, okay, so what I'm saying is B is smaller than A, but B by A is an integer, B is smaller than equal to, this implies belongs to Z, B by A is an integer, because by the definition of GCD, this implies that B equals A. So in this case, B equals A. But if B equals A, then LCM of A comma A is not 2A. It is equal to A itself. And this case you have already actually taken care, in this A comma A. So 2 comma 1 is actually not giving us a feasible solution. Okay, I'll just try to repeat for 2 comma 1 once. So if T equals 1, GCD of A comma B is equal to A. And by our initial assumption, A is greater than equal to B. So B is also equal to A. But now if B is equal to A, LCM of A comma A is A only. It's not 2A according to our, according to our given value of K. So this is a contradiction. So 2 comma 1 is not feasible. Similarly, if you take 3 comma 1, you'll get B is equal to A again, because T equals 1. Again the LCM will be A, but K equals 3, which is not possible, feasible. Sorry, I just erased it. Yeah. So this is also not feasible. So these are the possible cases. Fine. Okay. And now we want the number of ordered pairs. So A comma B and B comma A both have to be considered, because the problem is symmetric in A and B. So if A comma A by 3 is a solution, then A by 3 comma A is a solution. Similarly, A by 2 comma A is a solution. Now if A comma A is a solution, the reverse is also a solution. But reverse is A comma A itself, because both these are equal. So this is kind of like a single one. Okay. Now when will these numbers exist? Because we want them to be proper integers. So these numbers will basically exist when A is divisible by 3. a by 3 will be an integer, and when I say dividing here, it's a proper division, not the integer division. So a by 3 will be an integer when a modulo 3 is 0, and a by 2 will be an integer when a modulo 2 is 0. So basically, we want the number of a less than n which are divisible by 2. Okay, we want the number of n, a less than n which are divisible by 2, such that we get this one, that is n by 2, or in simple words, the number of even numbers less than n, that is n by 2. Similarly for 3, we want a by 3 to be an integer, so we want the number of multiples of 3 less than equal to n, so that is again equal to n by 3. So we can get this by n by 3. I'll change the color, it has become a lot very clumsy out here. We can get by this by n by 2, and this is also n by 3, because these both are same, and this is n by 2, and this is a comma a, so a is going from 1 to n, so you can take all a's from 1 to n, so this is again n possibilities to do this. So the answer will be 2 into n by 2 plus 2 into n by 3 plus n. So we can see the code for that. It's pretty direct, but I would still like to show it. Yeah, so n plus 2 into n by 3 plus 2 into n by 2, and I just print that. So yeah, I discussed the problem in quite a lot detail, but when you're solving the problem, you can do most of these cases in mind. So it's actually not that a lengthy problem as much as it took, because I'm explaining out here, so I need to explain in complete details. So it might have seemed lengthy, but yeah, it's a pretty much doable problem. So yeah, let's move ahead to problem B now. Okay, so let us move ahead to problem B. Now, problem B is saying that you have a square of size n by n, and every rectangle of any k consecutive vertical or horizontal cells. Basically, every rectangle of size 1 by k, there must be at least one x, and the thing contains dot and x. Okay, so what this says is that, suppose you put some arrangement of things. Suppose I put dot 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 x, x dot, some arrangement of dots and x's. Now suppose my k equals say 3. So any 1 by 3 rectangle I take, this might be like this, or this might be like this. Anything, any 1 by 3 rectangle in the whole matrix, in this whole matrix, any 1 by 3 rectangle I take must contain at least one x. Okay, so how do we think of this problem? So you see, suppose we take the first k elements. Okay, let us take the matrix of size k by k. The first matrix of size k by k. Also, one more thing is that n is a multiple of k. So if you take matrices of size k by k, you can evenly fill out the whole big matrix, because n is divisible by k. And I'll just like to erase few things to make it slightly less clumsier. Yeah. So suppose you consider this matrix. Okay. Now let us see the first row. The first row is a thing of 1 by k, because by we have assumed the matrix is of size k. Now we need an x in this. We want to minimize the number of possible x's in this. Okay. And also one more thing which has been given is that there has been cell r comma c given, which has a symbol x in it. Okay, so for time being, let us forget about this r comma c part. We'll come to this r comma c part later. But let us just try to find out. Suppose given an n, how do we get an ordering which has a minimum possible characters x, and this condition is satisfied? So suppose you take the first k by k matrix. Now in these k elements, we need at least one x. Okay, at least one x, at least one, at least one x out here. and we want the minimum number of x's. So the optimal thing would be to use one x. So suppose I use the x somewhere, somewhere in the middle, say. Let's not assume at the beginning or somewhere. Let's take somewhere in the middle. Now, what are the implications of adding this x? You observe that this x has not only covered this row, but it has also covered this column in this matrix. Now, if I take this column in the matrix, that also has one x in it. So that is also 1 by k, and that also has one x in it. So if I put 1x, it's covering one row and one column both. Okay, now we are supposed to do this for the second row. Now, either we can put the second x here itself, or we can put it some other place. Okay, so suppose I put the x here. Now this row is getting covered, but I observe that only this row is getting covered. We are not getting any additional column by this, because this x is covering this column itself, and this column has already been covered by the black x. So the red x is not giving any more advantage. Rather, if you put this x somewhere else, suppose we put the x here, not only will this cover this row, but it will also cover this column. So we are again, we are covering two things, a row and a column with this x. Similarly, we can do it for all things. So basically what is happening is that in every row we need one x, because we are putting only one x in every row, and in every column also we need one x, because we want to minimize the number of x's. So if you put 2x in one column, then that is basically repetitive, because that column needs 1x and you are putting extra x. So that will not be the optimal case. So it's kind of like, if you played the game Sudoku, it's kind of like that. You have to place one number such that, it is they present once in every row and once in every column. So let us find any way to do this. Okay, so one very trivial way to do this will be put all the x's along the diagonals. Now you see, every row has one and every column has one. Now this is a very trivial way to do it. And anyway, we just need to minimize the number of x's. So this works well as fine. Okay, so this is one way to do it. Now let us come to the original problem. The original problem says that r comma c also has an x in it. Okay. Yeah, okay. So I've not completed the whole part of the first problem yet. So this is considering the first k by k matrix. Now suppose I move somewhere ahead. Suppose I take the next k by k matrix. I again need to do the same thing. I again need to have a row of x's here. I take something else here. I again need to have a row of x's here, and so on. So this pattern basically has to repeat all around. If it's the first matrix, it has to come in the second matrix, third matrix, fourth matrix, and so on. So now one doubt might arise is that what if you take this matrix out here? Does this also have all x's properly? Does this also satisfy that every row has 1x and every column has 1x? This actually does so, because once you start repeating this thing, okay, I'll erase some things because it becomes slightly clumsy. Yeah. So if you take the next submatrix, the next x will come here. Next, this one will go outside and it'll continue like this till here. Now you see, the x we are leaving outside is the x which is coming in. I mean, the position of the x relatively remains the same. So even if we so this matrix also satisfies that thing, that every row has one thing and every column also has one thing. And this can be done for every sub k by k matrix. So if you come with such an arrangement, then that is always going to have this constraint true, that every among k consecutive things, every 1 by k rectangle contains at least one x. Okay, so I'll just give a gist of whatever I told again. So my aim is that I need to put one cross in every row and every column of this k by k matrix, because if I put any more x, I'll basically be repeating. And now I've got this k by k pattern, and I repeat this k by k pattern again and again. And since n is a multiple of k, so this k by k pattern will fill the grid completely. Now, within this k by k patterns, the k by k matrices, this condition is being satisfied. Now, how do we see, you know, uh, say rectangles which are half of one matrix and half of the other matrix? What this will, happen is, suppose you have arrived at this matrix from, say, this matrix, the x's you have left are the x's which are incoming. So there's not an issue. Now, you might also think that there might be a case where, the matrix I'm forming, that is the combination of 4 matrices. In that case also it holds to be true. What would happen is there, the things which you're leaving on the top will be coming from the bottom, and the things which you're leaving on the side will be coming, from the left side will be coming from the right side. You can just take an example to, see that thing also. So yeah, this is a case which is possible always. That you basically write this and you repeat this n by k times. Now it's also said that r comma c contains contains x. So suppose we made our initial arrangement this. Now okay, again let us consider only this k by k matrix. Okay, so r comma c can be obviously greater than k. So basically what I'm trying to do is r comma c will have a relative position in this k by k matrix. That is what I'm considering. That will be something like r modulo k comma c modulo k, something like that will be there. So I will have a relative position in its corresponding k by k matrix, and we consider the corresponding position in this matrix, in like the first k by k matrix, and then we can just repeat that thing again and again to get our answer. Now, suppose r comma c is already filled out here. Okay, so we don't need to do anything. We can just print the answer. This is the thing, because the question says r comma c, x should be written there. So if x is already written by this, then it's well and good. If x is not written by this, suppose your r comma c comes out to be somewhere here. So what I do here is I go through this column. Okay, this column will surely have one x, because every column has one x. What I'll do is I'll exchange these both things. Okay, so what will be the condition after this? The condition of the matrix is, and this box is empty. Now empty basically means dot, so I'm just making a box so that's more clear, more visible. Now you see, now you consider this row, the row, rth row, rth row, because it's an r comma c, so this is the cth column and this is the rth thing. Now the rth column actually is 2x's, which we know is not optimal, so we need to somehow change some things. And this x is constant actually, because it has been given in the question that r comma c has an x. So we need to change the position of this x. Now where do we put its position? Now observe that this row, okay, this row from where you removed the x has no x anymore. Because you removed the x from that row and there is only one x, there is no x in that anymore. So what I would do is that I would take this x and I would just put it in its corresponding position. So I basically go up like this. I go like this. And the point of intersection, I just swap these both x's. I swap these both positions. Now the condition of the array would be something like this. And so on. This will keep extending. Okay. Now you observe r comma c also has an x in it, and our initial proposition that every row need to have one x and every column needs to have one x is also satisfied. Now if you repeat this pattern n times, n by k times, our work is done. So that is basically the how to solve the problem. I'll again summarize the last part. You find r comma c, you see the cth column, you find the position of the x in that thing, and you swap these both. Now you can see the rth row, you find the position of x in the rth row, and you swap it with the intersection of that column and the corresponding row out here. So that is what I've written by code also. I'll show you the code. Yeah, so I take a character 2D array. Yeah, also first thing as I told you, I'm basically converting R and C to, its equivalent in a small k by k matrix. Like R comma C will be in some k by k matrix. And I'll just mention how my matrices are going. So my first matrix is the first k by k matrix, and my second is like this, and so on. And my and the next row of matrices start like this. So R comma C will be somewhere. It will be in some submatrix. So I'm basically capturing the relative position of this in this matrix. That is basically this modulo thing. I take a character array, and this is basically populating in our original way as we discussed. If this is the thing, we want to populate the access in this pattern. So I just see I modulo k plus j modulo k. Initially, I actually wrote the code thinking something else. So this mod k is after this thing does not make sense because r has been taken modulo k. So anytime you see something mod k, you can just safely ignore it because I is below k. So I modulo k will basically be I. So if I plus j is k minus 1, that is basically this row. I fill it with x's. Okay, I fill it with x's, else I fill it with the dots. Now what I do is, yeah, so in my explanation, I basically went through the column. In the code I've written, I just went through the row. Okay, both of them are completely identical. You know, what happens here is you go through the row, you find the position of the x and you swap. Then you go through the column and you swap that thing. Swap the uh, old x and the empty bracket. So I find the position of x. Now this part is actually redundant. You can just ignore it. I by k will always be 0 and c by k is also 0 because I have taken mod k. So if a of ri is x, I make pos equals I to store this. Okay, I'll just make another matrix. Suppose this is my r comma c. So to store this position, I store it in pos. Now I iterate through the column and I check I not equal to r. Basically, I don't want r comma c to be considered because r comma c already has an x because I've just now swapped them. And after that, I swap these both. So as we just discussed, a of I comma pos and a of I comma c. That is after you swap this board, you'll get something like this out here. And then you swap this one and the corresponding thing here. So that is what I've done in this part of the code. And then I basically just print this 4 times. Now there are 4 loops, so you might feel the complexity is going very huge. It's actually not that. It's O of n square in it. It'll be n by k into n by k into k. K's get cancelled. It's O of n square on. So this part is basically printing that pattern n by k times. Yeah, that was the code of this problem. Now again, I explained the problem in quite a lot of details. Probably my solution is not the best solution. But yeah, I use this to solve this in the contest. So yeah, let's move ahead to problem E now. I'll just open another sideboard. This has become clumsy. So yeah, so thing which has been given out here is that a plus b plus c is n, and you're supposed to find all these sum of all these possibilities. LCM of c comma GCD of ab. So you want sum of LCM of C comma GCD of AB. Now, and A plus B plus C is N. Now my first idea is that, since there's just one case given, I can have an O of n solution or O of n log n solution, O of n root n solution also. That is also fine. That'll still be within the constraints. The time limit will be sufficient. Now what my idea was, C is out here, and LCM of something, C comma something, this can be calculated in O of log n time. Okay. What we could, LCM is basically product of numbers by the GCD, and GCD you can calculate in O of log n time. There's an inbuilt function, or you can write the hard code the function also. So my initial idea was that let us try to iterate over all C. Okay. So we need to simplify this part in some way, so that we get a constant. Or, something like a root and order or something like that. Because if you see now, there are actually n square possibilities for this thing. If you fix A and C, B is itself fixed. Because A plus B plus C is n. So there are n square possibilities for this question. So it will take O of n square time, which will exceed the time limit. So basically evaluating all these possibilities takes O of n time. So can I shorten this time? Okay, so let us take C. So as I told you, there are two independent variables. So one of them let us consider to be A, and then you'll have. So I'm considering only this expression, A comma n minus C minus A. Now everything I'm considering is for a given C. So this n minus C is constant. For a given C, I'm iterating over all C. For a given C, C is constant. So it's basically K minus A. Now, what my claim is that this is also equal to the GCD of A comma K. Why I'm saying that? Okay, I'll probably just type down stuff. I think that would be faster in this question. So what has been given is that GCD of A comma n minus C minus A is what we are supposed to find. So I'm saying let n minus C is equal to some K. Okay, because for a given C, K is constant. N minus C is a constant, so let us take that as K. So now our problem is GCD of A minus K minus A. So if suppose this GCD is say L, okay. So this basically tells L into T1 is A and L into T2 is equal to K minus A. Now let us try to write T1 and T2 in both the methods. So by equation 1, so let's call this 1. Let us call this 2. So by equation 1, we get T1 equals A by L, and by 2, we get T2 equals K minus A by L. So this is basically K by L minus A by L. Now A by L is actually T1. So T2 equals K by L minus T1. So you can just rearrange this thing and we'll get L into T2 plus T1 equals K. Okay, so we have got, now let us take this to be equation 3. Now also one thing, in equation 1 and 2, T1 and T2 are co-prime. T1 and T2 are co-prime. The reason is that if T1 and T2 have some common factor, okay, if T1 and T2, so I'm getting L into T1 is something and L into T2 is something. So if T1 and T2 have some common factor, call that alpha, I can actually include this alpha in L only. So my new L dash is L into alpha. So that is contradicting because L is the GCD, so it's the greatest common divisor, and we are getting L dash is greater than L. So by that thing, T1 and T2 must be co-prime. Else we'll get that L is not the GCD. So now suppose T1 and T2 are co-prime, which implies T2 plus T1, comma T1 are also co-prime. Now, how does this happen? Now, suppose something divides T1, okay, because something has to, because we are considering one of the numbers is T1, it won't divide T2 because by definition T1 and T2 are sorry, by the proof we just did, no, T1 and T2 are co-prime. So if T1 modulo A is 0, if T1 mod A is equal to 0, then T2 mod A is not 0 for any A not equal to 1, which implies T1 plus T2 mod A is also not equal to 0, which implies T1 and T2 comma T2 plus T1 comma T1 are co-prime. Now all this I basically did to just prove one thing. My aim was to prove GCD of A comma K minus A is equal to GCD of A comma K. Now why this is really beneficial is that now you observe this K is a constant, so we can actually try to play something with it. So suppose GCD of A comma K, okay, I'll just type this part also. Suppose GCD of A comma K is say some L. So what will be the GCD of A by L comma K by L? Now if I'm saying A comma K is L, which means this is the maximum factor dividing. This is the maximum. So if I divide A by L and K by L, they will not have any more factors left. Okay. So GCD of A by L and K by L will be 1 because GCD of A comma K is L. So this is the maximum number dividing both A and K. So once I divide, A by L and K by L, there are no more numbers dividing A by these the new numbers. So since no the numbers are dividing, the GCD is 1. Now you know that A is less than K because n minus c is base. K is what? K initially is n minus c, that is A plus B. Okay, so K is also equal to A plus B. So A is less than K. So for a given K, so for a given K by L, you want to find all numbers F such that F comma K by L is 1. Now this is the definition of the Euler-Toshan function phi. Now what phi of n is, in case you didn't know, phi of n is basically phi of n is number of numbers less than n which are co-prime to. Okay, so this is what we want out here. A by L comma K by L is 1. So suppose we want to find the number of numbers which satisfy this. We want to find the number of numbers with GCD A comma K equals L. Now this will basically be equal to phi of n by K by L, because this problem is essentially same as this problem and the number of solutions of this problem is phi of k by L. So that is what we want basically. And this L, what can this L actually be? Now L is a factor of k, by the definition of GCD. So L is a factor of k. So you can find all the factors in root n complexity. So if you want the sum of numbers, it will basically be sum of this phi of k by L for all the factors. Now in our case, we basically want GCD of f comma sorry. Now in the original problem, what we wanted us LCM of c comma GCD of a comma k minus a. Now this will basically come out to be phi of n by k. Sorry. Phi of all the factors of k factors of k into LCM of c comma say this factor of k is say some I n by I. Why this is happening? Observe that for this thing we are having number of solutions for this thing is phi of k by L. So when you're iterating over all a's out here, so what will get is you will get this L phi k by L times. So you'll get LCM of you'll get something like LCM of c comma let's say the factor is I plus LCM of c comma the factor is I, and so on. You'll get this thing phi of k by L times. So it's basically this into the LCM, and we try to do it for all numbers and we sum it over, like we iterate over C and we get the factors in O of root n type. Now another major question is, how do you find the phi of n? Now actually I didn't know how to find phi of n during the contest. So I took the code from CB algorithms. That is perfectly allowed. You can use any code which has been written earlier and is public to everyone. So I've written the link also out here, so you can just check that thing too. So basically we want the phi of all numbers from 1 to n in O of n log n. Now it's basically kind of sieve, so the complexity also resembles the same. So I just took this function, I used it out here to find the ETF of all function, all the numbers till n, and this is an LCM function which basically finds LCM product by GCD. So I do ETF of n plus 5 because that is all the ETFs we are ever going to use. We are going to use ETF till n only. Now my sum is basically storing the actual sum which has to be printed. So I go from 1 to n minus 1. Why I go to 1 to n minus 1? C can go from 1 to n minus 1 because n minus C must be greater than 2, because A and B are greater than equal to 2. A and B are greater than equal to 1. So n minus C should be greater than equal to 2. So I have to go 1 to n minus 2. Not n minus 1, n minus 2. I have put a less than sign here. That is basically n minus 2. Now here basically I'm finding all the factors of n minus I. Our initial k was n minus c. So I'm finding that thing. So if k modulo j is 0, now I check whether the numbers are equal or no. Now I don't check for j not equals 1 because I don't want this to be exactly equal to n minus I, because in that case b will come out to be 0. which is not allowed. If A is exactly n minus C, then B is 0, because and the question states that all triplets of positive integers. Yeah, so I basically write what I wrote here in the notepad, or I think I wrote it out here. Yeah, 5 of the factors of k into LCM of c comma n by I. See if this is I. So v of k by g, I have just put mod everywhere, just to prevent any overflows. Probably these many mods weren't required, but I just put them. V of k by j into LCM of I by j, I comma j. Now v is basically phi out here, so v of I is LCM of c of n by I, or you can just flip n by I out here. You'll get something like this. Now this second part is basically for the other factor, so it's exactly this, phi of I into LCM of c comma n by I. Now if it's a perfect square, then j and k by j will be equal, so you just need to add the sum once, and in that case v of k by j mod m into LCM of I comma j mod m. You just have to do this thing once, and after every step I'm taking the remainder of sum by m, and I print the sum. So essentially, to give a gist of this problem, my first aim was to the naive solution of is O of n square. So if I can simplify this thing in some way, so that I make it O of n root n of, or O of n log n or something like that, that would be better. Now, we knew there were two dependent variables. So I took my k to be n minus c. So, which is a plus b. Now suppose, now what I tried to prove was GCD of a comma k minus a is GCD of a comma k. And for a given c, k is constant. That is the benefit of doing this thing. Now we gave a small proof for this. Now here, suppose we take GCD of a comma k is L. So a by L comma k by L is 1. Now this should remind us of the Euler-Torsion function, which is number of numbers less than n which are co-prime to n. This is basically phi of k by L. Now from here, I think it's obvious that you just need to write phi of k by this expression, phi of I into LCM of c comma n by I. Now yeah, this problem might have been hard because most people, or quite some people, might not know Euler-Torsion function. But sometimes what happens is you might have arrived at this thing, that you might have arrived at this position. Now, whenever you see something, very standardish type of thing, this is basically telling, this is a constant. It's basically telling that you want GCD of a comma b to be 1 for all, first you need to find the number of a's such that GCD of a comma b is 1. You can try googling this thing during the contest also, and you would find about the Euler-Torsion function there. I turned out, like, I knew this thing quite some earlier, like, because of preparation of Olympiads and all in my +1 and +2, but I didn't actually know how to implement it because I never kind of used it. So I took the implementation from here, and that is also all right. That's fine to do. And yeah, so that is what was problem here. So yeah, that's it from my side, and I think I over explained a lot of questions, but I guess I just felt that to repeat some points, and to make all the points clear. So yeah, if you have any queries regarding any of the problems I've discussed, or any suggestions over how I can improve, do let me know in the comment section. uh, yeah, thank you for watching.
Hello guys, this is Chahal here, and I'm my Codeforces ID is Chahal, as you can see, and now I'll try to explain problems A, B, C, and D of round 818 today. I'll explain problem C and D. My friend Anmol has explained you problem A, B, and D, and as you can see, I was able to solve A, B, C, D, and secured a rank of 423. So without any further ado, let's move on to problem C. So problem C, Madoka and formal statement. The problem is kind of interesting. Like they have defined an operation where you can basically increment AI, any index of the array, by one if I is less than n and AI is less than equal to AI plus one, or I is n and AI is less than a of one. Basically, you can consider the array as being circular, like the after the last element you get the first element, and then you're just checking that you can increment AI if your AI is lesser or equal to the next number. So now you need to see whether you can make another array B from this array AI, and the constraints are like n is 2 into 10 power 5. So any algorithm that you do that is not O of n won't give you the answer. AI is 10 power 9 and BI is 10 power 9. So you need to give an O of n or O of n log n solution for this question to get the answer. And like these are the test cases. So I'll first try to explain to the test cases. After which you can pause the video if you got an idea. Like I encourage you to pause the video and think. And then if you have an idea, then you should try to solve it using that. If not, you can continue watching the whole video and then solve it after that. So now let's move on to how the test cases are. So these are the five test cases. Now, if you see in the first test case, all the elements are directly equal of A and B. So in that case, it's obvious that we can do it, and the answer for this test case will obviously be yes. Now, basically, why are we solving the test case? Is because like if you just read the problem, it's hard to get an idea directly. But like while solving test case, you might come up with some observations or ideas, and those are useful to solve the questions. So like if you see the second test case, we have 2 here and we have 1 here in B. So the operation that we have defined, it only increments A. So there's no way that we can decrement A to become 1. Like we can't decrement, we don't have the operation only increment, so we don't have an option to decrement. So in this case the answer will be no. So we have seen that if Bi is less than Ai implies the answer is no. This is an observation we can get from this test case. Now moving on to the next test case, we have 3 in the first place and 6 in the second place. So obviously we'll have to increment 3 thrice to reach here. So let's see, we'll do it first. So this will become 4 and then 5. Like till 5 we can increment it. And then once it has become 5, it is greater than a of 2. So we cannot increment it further. And so it will never be able to reach 5, because like if we have to increment it, we need to increase the next value. And if we increase the next value, it will exceed 4 and then we can't come back to 4. So in that case, as we can see, the answer is no. And from this case test, we can sort of realize that if say AI is less than BI, then we need to check whether BI is like less than equal to BI plus 1 plus 1. We need this constraint because like say this is violated, then as you can see, it's not possible to create array B. This is because see, when the maximum value of AI plus 1 is always less than equal to bi plus 1 if it is valid, and if that's the case, then to increment AI you need it to be maximum bi plus 1, so you can increment AI to maximum bi plus 1 plus 1, so bi cannot exceed that. So this is another condition that we need to check. Now moving on to the next test case. So yeah, so here first we need to increment this twice, the first index, and that is rather trivial because this index is bigger. So once we do that, this first element becomes 4. So we have matched the first elements. Now if you see the last element also, it's 1, and we need to increment it to 3, and we need to compare it to the first element. So obviously we can increment it easily, and that becomes 3. Now if you see the middle element, it is bigger than this element, so it cannot be incremented, and we cannot make it equal to 5, and thus the answer to this test case will also be no, and this we know from this condition that we have derived here. Now the last test case. So uh, in this, let's start from. So firstly, we'll notice that we can increment all values. So we'll say we increment first we increment 4 and 5. So this 4 we can increment twice, it becomes 6. All right, so first so good, and then 3 we keep on incrementing till we reach 6. So one value has been matched now. Then we need to increment 2 till 5. So in that case, we can see that we can easily do that because it's less than 6. So we've done that, and then 1 needs to be incremented to 6. So we'll increment 1 till 5, and then 5 is equal to 5, so we can increment it till 6. So that is also matched. And now 5 will be compared to 6, so it can also be incremented. And then this 6 is equal to this 6, so that can be incremented as well. And as you can see, we reached array B from array A in this test case, and so it is possible here. And as you can see, this condition that we derived, it is holding on each of the values, like as you can see, and only then we are able to derive it. So this is a necessary and sufficient condition for our this, as along with this is a necessary and sufficient condition for us to be able to get array B from array A. And this is basically the logic. We need to iterate over the whole loop and check this condition and this condition as well. And if both are, and if the second condition both is violated, or the first condition is violated, then we'll output no, else we'll output yes. And this is basically how I've done it. So as you can see, this is my code. So first I've taken like the input n, and I've created a variable e. So e is basically e equal to 1 means that we can make array b from a, and e equal to 0 will mean that we cannot make array b from array a. So then we take array a and array b as inputs, as you can see, and we are checking the first condition that you mentioned, that bi is less than ai. So if that ever happens, we'll put e equal to 0, and e equal to 0, as you can see, means that we'll output no. Once that is done, we'll again go in loop, and this time we are checking if ai is less than bi. So if ai is less than bi means ai needs to be incremented, and we need to see whether it's possible to increment ai or not by checking this condition. And we are just checking it once more for the last element, because like for the last element we cannot make it circular directly, so we are making another if statement for that. Alternatively, you can do percent %n, that also works. So we'll check that also, and if it's 0 we'll output no, else we'll output yes. And this was basically the logic and code for the problem C. Now moving on, we'll move on to problem D now. All right, so problem D sort of talks about how an organization works and how there's a competition. And you can, so basically the gist of problem D, after you'll read it, is that you have a tournament which has 2 power n participants, and you need to create like the tournament tree of that tournament, and you can decide who wins at which place. But the thing is, you will get rewarded if the person with the lowest index wins. So ideally, you will want one to win, and that's how you'll make the tree sort of. But then the organizers are sort of, they're sure they don't want you to win, so they'll try to rearrange the they can change the result of k matches and all, out of all the matches that you have planned. And so these n and k are your only inputs, and you need to find out the maximum value, that the answer basically, the maximum index that will be the winner. So like, say we do 0 changes, then one will win because we are playing optimally. So in that case, we'll output 1, and that's what we have to output. So we'll be given n and k, and then we need to try out the test cases. So we'll first try out the test cases, and then we'll see what logic we can come up with. So the first test case is 1 comma 1. So that means that there are two participants in the tournament, one and two, and the winner of this tournament, we'll plan it to be one. Now the organizers come into the picture, so they'll try to increase this value as much as they can, but they can make only one change. So in that case, they'll just change the outcome of this match and make two winner. So in this case, the answer will be two. Now in the next test case, we have two and one, so there are four participants in all. And yeah, this is sort of the tournament tree for that. And we are playing optimally, so we'll always make one win in the first case, in the basic case, and then we'll just sort of like, let's assume that one came from the left side in both the matches. Now see, the organizers can do only one change. So basically, if they want to change the winner, they'll have to change the outcome of either this match or this match. These are the two matches whose outcome they can change to change the winner of the tournament. So basically, there are two vacant spots, and these vacant spots are distinct. So just to minimize, like we can put two in one place and three in one place because these two are the smallest number after one. And then say two came from left side and this came for right side, four came from right side. So this is sort of the tournament tree that we get, and the organizers can change either the result of this match or this match. And in that case, if they change the result of this match, three wins here, and three becomes the winner. So three is the biggest number which can become the winner in one change, and three will be the answer for this test case. Now for the final test case, we are given three and two. So there are a total of like eight players in the tournament. So we'll put that. All right. And yeah. So now we need to arrange the players in this. And as you can see, the organizers can do a total of two changes to what we can do. So firstly, we can see that the winner of the tournament will be one because that's we're playing optimally, and we are assuming that one came from left side. That's like without the loss of generality. You can take it to be some other path also, but in the end, that's how it will work out. So let's take it from the left completely. Now, firstly, in one change, to change the winner, the organizers can either change the outcome of this match, or this match. And so we'll try to minimize that thing first. So there are three distinct boxes here. So we'll put 2, 3, and 4 there. So let's put 2, 3, and 4 here. So from this, we know that the answer for the test case 3, comma 1 is 4 because they can just change the outcome of this match and then 4 will win the tournament. Now the organizers can obviously do the second change also, and we are assuming that the winners came from left. So 3 came from left, 2 came from left as well. So now to change the winner again, like say they want to change the winner so much that, so if they change the outcome of two matches, so basically say they change the outcome of this match, they can change the outcome of this match also to change the winner. Similarly, they can change the outcome of this match, and then they change the outcome of say this match or this match. In that case, also the winner will change. So there are a total of one, two, and three boxes here. All are distinct, as you can see at different levels. So we'll try to minimize that also by putting 5, 6, and 7. And then we are left with 8, so we'll put 8 here. So as you can see, if we are given 3 and 2, the organizer will first change the outcome of this match and then change the outcome of this match to make 7 the overall winner. And in that case, 7 will be the answer. And here, as you can see, so basically, if we were allowed one more change, say 3-3, then we can see that we can change the outcome of this match also and make 8 win. So one thing that we can notice from this is if we are given n comma n, that is we are allowed to make n changes, then we can, the organizers, so they can just change a match on every level, as there are like a total of n levels here, and make the lowest person, the highest person, the winner. So in that case, the answer will be directly 2 power n. So we have covered that case. Now, say the number n is smaller. So one more thing that we can notice is if it's n and 0, that is we are allowed 0 cases. In that case, 1 is the winner, obviously. Now, say we allow one change. So as you can see here, this will be a graph of n levels, and on each level, as you can see, there is one match whose outcome the organizers can change, and using that they can make another person win, which is a total of n possibilities are there. So in that case, the answer will be n plus 1. Now, in the next case, say we are given n and 2, which is like 3 and 2 in short. So there are n levels here again. Now, in these n levels, we can choose any two levels. Say I choose this level and this level, or like basically you can choose any two level. Okay, like this level, or this level and this level, and then change the outcome of appropriate matches there, and that way you will be able to create a new winner. And there are NC2 ways to do this. So in the case of NC2 ways to choose the levels, and then appropriately the winners will be changed. So in the case of n comma 2, the answer will become n plus NC2 plus 1. And as you can see, this method can be generalized up to k, and you'll notice that the answer for say n comma k will be 1 plus n plus nc2 plus so on till nck. This can be proved via induction, like you can apply that method inductively, or you can just take it for granted for now. And so basically using this, in a total of k changes, you can make the person with this index the winner if the organizers are really smart. And this is basically the answer. As you can see, this will match all the test cases. Like if you put 1 comma 1, you get an answer of 2, 1 plus 1, and so on. Like you can check for each of these three test cases and it will pass. And this is basically the code for problem D. So this is how we have coded it. Like the tricky part here again is calculating NCR, because the answer can go very big. So this is basically my driver function, which will take the pass it here. Then we are taking in n and k, and first I'm taking answer to be 1, because basically if you do 0 changes, 1 is the answer. Now what I'm doing is for every change I'm adding NCI and then taking the mod and then outputting the answer. That's all I'm doing. And to calculate NCR, basically this is sort of a template function that I keep with myself because it makes my life sort of easier. So what I do is I calculate the uh, like the answer P is first n factorial divided by r factorial into n minus r factorial, the basic formula. And for this, I've used another function factorial, as you can see, factorial mod. And this factorial mod basically creates a vector of factorials which stores all factorial from 1 to n. So we are sort of pre-computing all factorials from 1 to n. So that will take us O of n time, and after this O of n time, we can just access any factorial in O of 1 time. So we are calculating each NCR in O of 1 time and then adding it. So a total of, and we are computing n factorial only once. That will take us n operations, and this loop will take us minimum of n comma k operations. Why have we taken minimum of n comma k? Because say k exceeds n, then NCR doesn't have any meaning, and we haven't handled that case separately in our function, so we are just taking it this way. And that is the overall gist of this question, and we'll just output the answer, and that's all. I hope you enjoyed this tutorial, And now my friend Anmol will take over. That's all. Thank you. Bye.